Welcome to part 2 of Optimizers in Neural Network video. There is a part 1 of this series. The link is right here and in the pinned comment as well. I'll paste the link in description also. That is a mandatory video for this one. But in this one, we will dive deeper into the next 3 optimizers and we will finish the optimizers in neural network. So without any delay, let's try to understand what are the critical components of most advanced optimizers in neural network. So as part of part 2, we are going to do little brush up of what we learned in the previous video, and then we are going to fill these 3 blocks here. 1, 2, 3. Okay. So today we are going to learn about 3 more optimizers. Previously we learned about these 3 optimizers. Okay. So just a refresher guys, what is the difference between gradient descent, momentum and NAZ? So basically gradient descent is your plain vanilla optimizer and there are few variants of gradient descent. So it can be either stochastic gradient descent or it can be something like mini batch gradient descent, right? So these are different variants of gradient descent, but more or less these are same thing. It is basically plain vanilla updation of the weight using the gradient and the learning rate. Okay. Now, how momentum is different from gradient descent is if you go to gradient descent and just add a velocity term. Okay. So I will keep it like a story so that you can remember. If you just add a velocity term here, that becomes your momentum. Okay. So we have discussed this in detail in the last video. Now, how nag is different from momentum is basically just one addition on top of momentum, and that is here you use a concept of look ahead weight. Okay, so I will say concept of look ahead, look ahead. So if you add one simple concept here on top of momentum, that becomes your nag. That is the just basic differences between how gradient descent, momentum and nag are different. How momentum behaves differently than gradient descent. So basically gradient descent can take more time to converge right from the beginning till the end, right? So suppose if you are running an optimization for 100 iterations, right? You will see that gradient descent behaves differently than momentum behaves differently than nag behaves differently. So what momentum will do is it will simply give you push in the right direction and towards the end it may take time to converge, but initially that push will be fast. Okay. In terms of nag, what will happen is since there is a characteristics of look ahead, so it may converge faster. It may converge in lesser amount of time as compared to momentum. Let's see what I'm talking now. Let's see with one simple example here in Python. Okay. I will give you this code. Don't worry about the code. Okay. I will give you this code. Just don't worry about the code. Just think like here what I'm trying to do is on the y-axis I have parameter value. On the x-axis I have how many iterations. And as you can see here, it is converging close to 0. This line is converging close to 0. Okay. So let me increase number of iterations to make it simple. For example, if I make 400 iterations or 500 iterations also, right? You will see that the value at which it is converging is close to 0. Okay. And even if I make it 100 iterations, right, you will see that the value it is converging is at close to 0. Okay. Now, in the theory, I was telling you that if you run 100 iterations for gradient descent, it may take more amount of time as compared to momentum because momentum pushes it in the right direction in the beginning only. So right now I am running a gradient descent. So as you can see, 0 to close to 10 it is here and then close to 20 it is here, right? If I change this to momentum, right? If I change this to momentum, what you're going to see this not in the 10 but close to 3 4 iterations only. It come from we are starting from 10. If you see carefully, okay, we are starting from 10. From 10 it is coming all the way to minus 7.5 or 8, something like that, and then it again goes back to 7.5 plus and then it again, so slowly it is coming close to 0. Okay. What is happening in this case, how it is different from normal gradient descent? Normal gradient descent basically is kind of slow steps it is coming and trying to converge. Momentum, what is happening is it is getting a big push in the right direction. Then again, one big push in the right direction. Then again, one big push in the right direction. Okay. So one push, second push, like this. Okay. So momentum is basically speed. So that is what momentum does. Now, how nag is different? So as I was telling you, nag is basically, if you see, momentum is also converging in close to, it had started coming to zero, but towards the end it is taking more amount of iterations towards the end. Okay, but nag will solve that problem. See here, so nag is not taking that much of time in coming to 100. Okay, so if you see here coming to zero, I'm sorry, the gradient descent, right, close to, let's say, 15-20 iterations, it is stabilizing at zero. Momentum, which should be faster as compared to gradient descent, here I am running 100 iterations, it is gaining the speed, but in the end it's taking more time. It can happen, don't worry, it can happen. Okay, but it is getting the speed, that is important. And in case of nag, right, what nag does is it simply uses the concept of look ahead. And so if you can see here, right, around 10 iterations only it is coming to zero. So nag is doing very good. In the first or second shot only, from 10 it is coming all the way to -2, then adjusting itself and then coming to zero. Okay, so how these three optimizers are different: gradient descent, plain vanilla, it will just keep moving based on gradient and loss. Momentum is for speed, nag is for look ahead. Okay, out of these three, nag is supposed to work better in most of the scenario. With that in mind, let's move ahead and try to understand another optimizer known as Adagrad. Okay, Adagrad. In Adagrad, right? The word Ada stands for adaptive. Adaptive. Okay. What happens in Adagrad is your learning rate, right? We have been fixing the learning rate all this while. So in my Python thing also, you will see there is a parameter for learning rate, which I can increase or decrease. Okay, like this. But if you see here, right, learning rate in on our previous optimizers, for example, this one, and this one was not changing. It is fixed. Okay. But adaptive gradient, what it does is it uses a concept of varying or changing learning rate, which means that learning rate can increase or decrease. Okay. How that will be useful? Let's try to understand with a simple example again. Let's say this is your loss function. Okay. And this is your, let's say, theta. And your loss function is something like this. So suppose in gradient descent, you start moving in this direction. You start moving in this direction. You start moving in this direction. Okay. And your gradient is fixed. Sorry, your learning rate is fixed. So the size of your steps, right? This distance and this distance and this distance and this distance will depend only on the gradient. Okay, because I was telling you in the last lecture, right, step size is a function of basically what? Learning rate and gradient. Okay, learning rate and gradient. Step size is a function of learning rate and gradient. Correct, basically a multiplication of these two. So if your learning rate is fixed, right, suppose this part is fixed, suppose this is A and this is B. When you multiply A with B, and when your A is fixed, right, then your step size will only depend on the gradient B. Okay, I don't want this to happen. I will tell you what is the problem here. The problem here is, when what I want ideally to happen is, I want I want my system to move faster when it is here, move faster when it is here, and become slow when you are reaching the minima. Become slow when you are, this is the minima, you can think like this. Become slow when you are reaching the minima. So what I want to achieve is fast, move fast in the beginning and move slow in the end. Okay. When I say move fast or move slow, I am talking about the step size. Okay. How I can control step size is by gradient and learning rate. Okay. Now I ask you a simple question. In a function, let's say C is a product of A and B. Just an example, okay? I want C, the step size, to adjust based on the learning rate. What I want? I want the C, which is my step size basically, to adjust the learning rate based on the gradient. Okay, so what I'm trying to achieve here is, if my gradient value is very large, okay, if my gradient value is very large, then make my learning rate as small. And if my gradient value is very small, then make my learning rate as large. That is what I'm trying to achieve here. Okay, what I want is, I want my step size to change based on where the current position is. Okay, as I explained you here. How I can achieve that is, I can change my learning rate based on the gradient. So when my gradient is large, I want learning rate to be small and vice versa. How I can achieve this, mathematical formula behind this is, I will just write here from my note, gt, okay, is equal to gt minus 1 plus gradient of j theta square. Okay, I'll explain you in a moment what is this. And then theta is equal to theta minus alpha, which is my learning rate, divided by square root of gt plus epsilon j theta. Okay, here please try to understand this gt. Okay, this is called accumulated gradient. Accumulated gradient. Okay, accumulated gradient. Now, what will happen due to this is, what I'm trying to do here is, I'm trying to take into account my previous value of gradients. Okay, and in every step, this GT will get updated. Okay, suppose previously the GT was 0.008. Next iteration, the GT could be 0.009. Next iteration, the GT could be 0.0095. So what will happen is, in every iteration, right, my accumulated gradient value will keep increasing. When this increases, right, when this increases, what will happen to this part? Please pay attention here. What will happen to this part? When it increases, right, that means denominator increases in this red box. When the denominator increases, then this, what you see in the red box is updated learning rate basically. Updated learning rate. Okay. In this red box, what you see is updated learning rate. Just visualize how we are updating the learning rate. What we are trying to do is, we are trying to increase the value of GT with every iteration. When that increases, then the value of this increases. When the denominator value increases, the value of this entire red box will decrease. Denominator increase means learning rate decrease. So what you are achieving here? You are achieving high value of gradient and low value of learning rate. Okay, and that will adjust your step size. Rest of the thing remains same. So in normal gradient descent, theta is equal to theta minus alpha times of derivative of loss. Here you are not taking alpha, rather you are normalizing alpha, or you are adjusting alpha based on accumulated gradient. Okay, and when you are doing that, right, what is happening here is, you are simply adjusting based on the value of the gradient. Okay, so that will give you the benefit of, when you come to this diagram here, right, that will give you a benefit when you reach to something like this point, right, this point. What will happen is, your accumulated gradient will be high, hence your learning rate will be low. Okay, so your step size will automatically adjust accordingly. That is why we call it Adagrad, that is adaptive gradient. Okay, in what kind of situations this particular thing is useful, and in what kind of situations this is not useful. So basically, in your data, when you are dealing with sparse matrix, okay, when you are dealing with sparse matrix, when you have lot of features in your data, okay, so I'll just refer to my notes. When you have sparse too little info about certain features, so it can happen that there are different features in your data, f1, f2, f3, f4, etc. Okay, about some features you have very limited information. So let's say there is null, okay. You don't have a lot of information about some feature. You don't know how the gradient should behave, how the weight should adjust, right? What you should do is you should use Adagrad, okay. And the problem with Adagrad is, the benefit is you no need to update learning rate manually. It will update automatically. The problem is when it reaches towards the lower gradient area, right? For example, when it reaches towards, when this gradient, cumulative gradient becomes too high, right? GT value becomes too high. What will happen is this alpha becomes too low. When alpha becomes too low, then theta will not get adjusted only. I mean, in the end, right? It will not converge properly. That is the problem here. So once your GT becomes too large, then the convergence will not happen properly. So let me go to this chart here and try to show you. For example, I'm taking Adagrad here, okay? So as you can see here, it is coming from 10 to around 7.5, and into it took 100 iterations, okay? Let me increase number of iterations. I'm increasing it to 260. I'm increasing it to 380. I'm increasing it to 440. I'm increasing it to 490 or close to 500. Still the convergence to zero has not happened. And the reason for that is, every time I'm increasing the uh, I'm increasing the number of iteration, right? Accumulated gradient is value increasing, the step size becomes really low. So in the same thing, you saw that nag is doing wonders in very few iterations, right? But Adagrad is not able to do wonders in this scenario. That does not mean it will not be able to do in any scenario. In this scenario, I'm just trying to show you, since the step size is adjusting based on previous gradient, so the movement is very slow and it is not converging, okay. So let's go ahead and try to fill our box here, and I will call this as Adagrad. And Adagrad is altogether new kind of implementation. And what happens in Adagrad is basically learning rate decay. Okay, learning rate decay, because learning rate changes over time. Okay, so this is a new concept in Adagrad. Now, on the basis of Adagrad, there are shortcomings in Adagrad. Okay, so basically, what the shortcoming is basically, as I told you, right, when you reach towards the lower end, then your this value will be very high, and your accumulation or convergence will be very slow. Okay, so researchers have come up with another optimizer here, and they have named it RMSprop. Okay, this is basically slightly different only from the Adagrad. And let me give you the formula first. It's basically very minor changes compared to Adagrad. I'll just write the formula and make you understand. So this stands for RMSprop. Okay, root mean square prop. What happens in RMSprop is GT. Okay, GT, that is your accumulated or cumulative gradient, is equal to beta of GT minus 1. If you remember, previously we were not using beta in the Adagrad, and 1 minus beta theta, uh, derivative of loss. Okay, and then rest of the thing remains same. Theta is equal to theta minus alpha of underscore gt plus epsilon. I forgot to explain you why epsilon is added here. Basically, it's very simple to understand. Here we are trying to divide alpha by something, and suppose if this gt becomes close to 0 or 0, then a 0 division error will come. Okay, so epsilon is a very small number that is put in the denominator just to save into that situation. Okay, it's a very simple thing to understand. A small positive number to save you from 0 division error. Okay, so this is about this, and then whatever we learned in previous one, right, the same thing will come here. Now if you pay attention here, guys, RMSprop is different than Adagrad by just these two things, beta and 1 minus beta. What we are trying to do here is basically we are trying to ensure that previously, if you remember, I was telling you that here we are squaring the previous gradients. Okay, here we are squaring the previous gradients, and hence there is a fear of in the end this cumulative GT becoming too large. Okay, here also we are squaring the previous gradients, but what additionally we are doing is we are assigning a weight to this component. So basically our function is made up of two components. First component, second component. First component is previous gradient, previous accumulated weight gradient, and second component is this one. So suppose if you say beta is equal to 0.95, then this will become 0.05 and this will get less weightage. The second term I'm talking about. This will get less weightage. And this is the one responsible to make your gradient very, very high. Okay. So when you give a beta term here or when you adjust that, what you are trying to do is you are trying to use the concept of something very similar to moving average or exponential moving average, and you are trying to adjust the weight and give less weightage to this square term because you are afraid that it may shoot up your gradient value by too much. So you give less weightage to this and more weightage to the just last observation of this. Okay, the rest of the things remain same. So if I go to Python again and if I change this to RMSprop, right, i'm not I'm not anticipating any wonders here, but if you see here, right, after 100, so in your previous one, right, let me decrease, then it will be easy to see. Let's make it iteration 300 and see Adagrad. Adagrad, as you know, right, our value is 0 where we want to reach. In nag it is reaching to 0. Okay, 0 is where we want to reach. In Adagrad, you see that it is not able to reach 0 even after 300. We saw in 500 also. In RMSprop, we are able to see that near to 100 iterations, right, it is coming to 0, close to 0 at least. Okay, and if I make it 500 iterations, right, then still it is coming close to 0. Okay, so it is hovering around 0 basically. It is not still not becoming stable, but at least it is near to 0 after these many iterations. So what is RMSprop giving you is basically RMSprop is trying to give you a more stable version of something known as Adagrad. Okay, so Adagrad, what may happen is your learning rate may be too less that your adjustment itself stops or your step size itself is negligible. Okay, RMSprop protects you from that. So here I am writing RMSprop, okay, addition on top of Adagrad protects from step size becoming 0 or close to 0. Step size I'm writing becoming close to 0. This protects you from that. Okay, and RMSprop is normally working better than the Adagrad in most of the scenario. Now what we are going to learn is the most sophisticated and most used optimizer in the world of deep learning, known as ADAM. Okay, so what I'm going to do is I'm going to write here the formula of ADAM, but I'm going to tell you the story so that you can remember ADAM very, very clearly. So what we are achieving till now is basically you saw that from the concept of momentum, we are able to move in the right direction fast. Okay. And from the concept of learning rate decay or weight decay, we are able to adjust the step size properly. Okay. So what we are trying to do here, we are trying to see what all we have done in first optimizer, second optimizer, third optimizer, fourth optimizer, fifth optimizer. Okay. What we are doing in Adam is we are taking best of all these. okay, and combining it and calling it Adam. So Adam is basically a combination of momentum. I will just give a tick here. Momentum plus RMSprop, and in what context? From momentum, it will take speed. From momentum, it will take speed, and from RMSprop or Adagrad kind of thing, it will take decay concept. Okay. From both these concepts, if you mix it together, right, what you get is Adam. Let me write the formula here, and then it will be very clear to you. So, how Adam works is basically, in Adam, there is a concept of first moment and second moment. So, what I'm writing now is called first moment. Okay. First moment captures the moment part. So, if you remember the momentum part, I'm sorry. If you remember the momentum formula, this is what something similar we had done. Okay. And this is called second moment for Adagrad. If you remember the RMSprop formula, okay, this is what we have done. Okay. So this one, right here, it should be B1, actually beta 1, sorry. Here it should be beta 1. This part is taking care of your speed, and it is coming from momentum formula. So if you watched my previous video, right, you can just see the momentum formula once. It is very similar to that. It is coming from the momentum. Okay. And this bottom part we just wrote now in RMSprop. So if I just scroll up a little bit, right, you will see that this is what is happening here. I'm talking about this equation. Okay. So it is taking speed and it is taking decay both. Once it has speed and it has decay both, then it will simply adjust the weight like this. Theta is equal to theta minus alpha times mt by vt under root plus epsilon. Okay. So this is the formula for Adam basically. This is called first moment and this is called second moment. And the value of beta 1 given in research paper or recommended is 0.9. The value of beta 2 given or recommended in research paper is 0.99. So what we are doing basically in Adam is, if you have understood how speed and decay works, right? This is basically a combination of these two, nothing else is there. Okay. One more concept before we wrap up Adam is, in Adam, you use the concept of something known as bias correction. And how bias correction works is basically, from MT, internally a new term is derived, that is MT by 1 minus beta 1 T. Okay. And from Vt, one new term is derived, that is called Vt by 1 minus beta 2 T. Okay. These are derived to protect you from something known as problem of starting with 0. Okay. Because when you initialize things, you will start with 0. And if in place of MT and VT, I use this concept is called bias correction. They may ask you in the interview, why bias correction? Bias correction, because in most of the cases you may start from 0. You may want to start from 0. In that case, I don't want the convergence to not start only. Suppose this is 0, right? MT is 0, suppose. Then what will happen? If MT is 0, then what will happen? This will never get changed, right? This term becomes 0. Okay. Similarly, there will be problems when VT is 0. So we don't want that to happen. So basically what we do is, we do a bias correction to start with, that will help in the starting the journey. Okay. This is about your Adam here. And as I was telling you, Adam is simply a combination of your previous optimizers, which are doing the good job. So if you don't know any other optimizer, or if you don't know which one to use, just use Adam. Okay. Now let me go here. and try to select Adam to see what happens. So if you see here, Adam is giving you Adam is converging at how many iterations? Let's see by reducing it. Adam is taking some more iterations, but again, in case of Adam, you can adjust these things. So let's adjust that beta 1, beta 2, whatever values I told you just now, right? Beta 1 0.9, beta 2 0.99. So 0.9, 0.99. The same value is given actually, but let's change a little bit and see what happens. Something is happening, something is changing. Okay, so things may change slightly when you change the parameters. I will definitely give you this code and you can practice and you can, play around with the things. I will just give you a revision of all two videos in just 2 minutes of time. Okay, so what is optimizers in neural network or deep learning or machine learning? Optimizers are basically a way to minimize your loss function by adjusting the parameters of your model. Okay, it's a difficult concept to understand because a lot of mathematics is involved. But if you have paid attention to my last video and this video, it will be a cakewalk for you to understand this. I have given a lot of explanation on all this. If you remember all these right, nobody will ask you to write mathematical formula in 99.9% of the interviews. They will only ask you how these things work and how they are different from each other. And the answer to that lies here itself. Gradient descent, basic, simple. Theta is equal to theta minus alpha time learning rate. Okay. And if I go and add a momentum term, that becomes momentum. If I go and add a look ahead term, that becomes nag. If I add the concept of learning rate decay, that becomes a Adagrad. If I do a square of that in accumulated thing and do a beta and 1 minus beta basically, then it becomes RMSprop, and Adam is nothing but combination of speed plus learning rate decay. Okay. Please don't forget to like this video and share with your friends if you feel this video is useful, guys. I'll see you all in the next video. Wherever you are, stay safe and take care. I'll also share the other Python file that I was showing you that day in my GitHub. Okay, both these things. Thanks everyone for watching. See you again.